welcome to Virtual Class 5. Today is Thursday, April 16th. Let's take a look at today's headlines. So, number 1, we are not watching the full video. If you notice on the graph behind me, I looked at some of the analytical data for the YouTube videos that I've been recording, and I've noticed that the time that students view the videos trails off. So, when I made a 30-minute video, we watched it for about 15 minutes. I made a 25-minute video, 10 minutes. Made a 10-minute video, 6 minutes. Made a 6-minute video, and we dropped down to 3 minutes. So I'm going to try something different to add a little life to these videos and hopefully get you to hang on to your attention for a little bit longer. Today we're going to be talking about the ideal gas law, PV equals nRT. The ideal gas law is special because it relates together pressure, volume, and temperature, which we've been learning about over the last week, and one of our good friends, the number of moles. So you can start to see where this is going to fit into our larger picture as part of our bridge between the moles of reactant and moles of product. But we're a few weeks away from that. I do want to take a minute and just look at the variables that are involved in the equation because it's important that we understand what they all mean and what units they carry. So our first variable, which is pressure, must have units of ATM. So if we're given a problem and pressure is in a different unit, we're going to have to convert from whatever unit it is into ATM in order to carry out our calculation. The second variable is volume. Just like pressure, volume has a specific unit. It has to be in units of liters. Now as we travel across the equal sign, we look at our last three variables, which are N, R, and T. So the first one, N, is the number of moles. That is going to be our bridge. And our last two variables, R, is something called the universal gas constant, and T is temperature. And just like before, when we're working with temperature, we have to make sure that we're using temperature in units of Kelvin. So if a problem gives us a temperature in units of Celsius, we're going to have to convert that to Kelvin before we can use it. Brings us to our next segment. What is R? If you look at the graphic, you can see that PV is equal to nRT, where P is pressure, and that's measured in atmospheres, V is volume, that's measured in liters, N is number of moles, obviously measured in moles, and T is temperature, measured in Kelvin. Now if you think about it, the units on the left and the right side have to work out to be the same thing. So in order for the units on the left, which are ATM and liters, to work out to be the same thing as the units on the right, which are currently moles and Kelvin, we need to get rid of the moles and Kelvin on the right side and add in the ATM and liters on the left side. So we wind up with our fraction liter times ATM divided by moles times Kelvin. And that's what R is. Okay, now I'm going to turn it over to me at the big board doing a sample problem, and we'll finish up with this. Thanks, Kevin. Let's take a look at today's sample problem. If I have 2.4 moles of gas at a temperature of 97 degrees Celsius in a container of 45 liters, what is the pressure of that gas in millimeters of mercury? Okay, so let's break it down. We're going to start off by writing our equation. So we have PV equals nRT. And they told us a bunch of information, so let's take a look at each part. In the first part, we're given 2.4 moles. So we know that N is going to have a value of 2.4 moles. We're looking for pressure, so we don't know what that is, and we're told that the volume in the system is 45 liters. So V is going to equal 45 liters. And that's already in the unit that we need, so we can move on from there. We have R, which I'll talk about a little bit more in a second, and we have our temperature of 97 degrees Celsius. So 97 degrees Celsius, but remember what I said about R. R needs to be in units of Kelvin, so we have to change that 97 degrees Celsius into Kelvin by adding 273. Now, since the 97 has no decimal places and the 273.15 has 2, our final answer for this will have 0 decimal places. So this will end up being 370 Kelvin. Now, back to R. In the last segment, I told you about R and we went over what the units would be. But R is a constant, which means that it always has the same number and the same units. So I'm going to tell you that the number that you're going to use for R, every single time that you see an R in a problem, you're going to use 0.0821. And remember, the units for that are liters, ATM, over moles times Kelvin. So, looking at this problem, I'm trying to solve for pressure. So I need to isolate pressure. I need to get pressure by itself. It's already on top, so we don't have to worry about moving it. However, volume needs to get out of here. So we need to shift volume across the equal sign. So we wind up with our equation P equals nRT divided by volume. Now we're going to plug in our numbers. So for moles, we have 2.4. For R, we have 0.0821 liter ATM over mole Kelvin. Remember, anytime you're working with R, you're going to plug in that number. The reason why we need specific units when we're dealing with the ideal gas law is because of R. Because R has these units and we need our units to cancel out, we need to make sure our pressure, volume, and temperature match up with the units that we have in R. If I continue, I have 370 Kelvin, so that's going to be in this last part here. And then we're going to divide the entire thing by our volume. In this case, our volume is 45 liters. Notice, two significant figures, 3, 2, 2. So I'm going to wind up with just two significant figures when I figure out my pressure. So my pressure in this case is going to be 1.6 atmospheres. But wait, because the problem specifically asked us for the pressure in units of millimeters of mercury, we now have to go back and change our unit of pressure, 1.6 atm, into millimeters of mercury. So to do that, we have our conversion from a couple of weeks ago. 1 atm is equal to 760 mmHg. And after I do this pressure conversion, I'm going to multiply 1.6 by 760. I'll get 1260, but I'm limited to 2. So 1260 mmHg, that's going to end up being just 1300 mmHg. All right, that's all for today. Tonight, your homework is to try problems 5 and 6. So I'll write that up here. Homework numbers 5 and 6 only. All right, thanks very much. Back to you, Kevin. Thanks, Kevin. Well, that's it for today. I hope everyone enjoyed this. Please remember to try problems 5 and 6. They can be found in the Unit 8 folder on Schoology, and save your work as a PDF, submit it using the Dropbox, and you're good to go. All right, let me know if you have any questions, and I'll see you next week. Thanks very much.